All right, looking at lesson 524, probability tables. You will notice at the top here there is an answer key to check your 523 work if you'd like to see how accurate and precise you are. I had a little technical difficulties with the video program yesterday or last time, so wanted to make sure you could do a quick check-in if you wanted to. We are working on lesson 524 video here, and again, watch it all, watch what you need. Remember to pause and replay as needed. Today we have a problem with a person named Gerald. He decided that his method was taking too long, is all too confusing, and that he made too many mistakes. Even if he listed all the combinations correctly, he still had to find the sums and then find the theoretical probabilities for each one. Inspired by multiplication tables, he decided to try to make sense of the problem by organizing the possibilities in a probability table. Remember, when it's blue, it's usually a hot link or a hyperlink to a definition or explanation, like the one shown below. So here we have our or Gerald's probability table. This is a great way to organize information if it is something that is in small enough data samples. The first thing it asks us to do is to fill in the empty cells, and it's an addition table. So if you notice the pattern, 1 plus 1 equals 2, 2 plus 1 equals 3, 3 plus 1 equals 4, 4 plus 1 equals 5, 5 plus 1 equals 6, 6 plus 1 equals 7. Let me do it again, only now we're adding 2, and we get 2 plus 3 is 5, 2 plus 4 is 6, 2 plus 5 is 7, 2 plus 6 is 8. Next, we're adding 3, plus 1 is 4, 5, 6, 7, 8, and 9. 1 plus 4 is 5, 6, 7, 8, 9, and 10. Some of you are seeing the pattern that comes on the diagonal here. We have the 6, 7, 8, 9, 10, and 11. 6 plus 1 is 7. 8, 9, 10, 11, and 12. All right, so that's done. How many total possible number combinations are there for rolling the 2 cubes? Well, we've got 6 by 6, so that makes 36. Is each combination listed likely, equally likely? And as I look up here, I see 1, 2, 3, 4, 5, 6 ways to get 7, but only 1 way to get 12, 2 ways to get 3. So I'm going to say no, they are not equally likely. And then here is a place where some of you should pay a little bit closer attention, because as some of you have been filling out the theoretical probability for some of our previous work, you forgot to list the theoretical probability as a fraction, a decimal, or a percent. And those are the correct ways to list the probabilities. So the theoretical probability for getting each sum listed would be written as follows. This would be 0 out of 36, or simply 0 for that one. This one, there's only 1, 2 out of 36 possibilities. For the next one, there are 2 3s. And I'm taking this information from the table up above. Probability of getting 4s, 1, 2, 3 out of 36 possible. 5s, 1, 2, 3, 4 out of 36. 1, 2, 3, 4, 5 out of 36 for that. Probability of getting a 7 is 1, 2, 3, 4, 5, 6 out of 36. 8 is 1, 2, 3, 4, 5. 9s is 1, 2, 3, 4. 10s, we have 3. 11s, we're back to 2. and 12s, there's only one chance out of 36. Can you reduce these? Absolutely. I chose to leave them all the same. It's a little bit easier to compare them when they all have the same denominator. All right, moving to the next problem that we are going to go through together. We have a person that is at the state fair and she decided to buy a sundae from an ice cream stand. The ice cream stand had 4 flavors of ice cream. You'll see that on this table, I've written the 4 flavors of ice cream down the left side, and they're listed chocolate, vanilla, mint chip, and coconut, and 2 toppings. I know that's hard to read on my print here or my paper here, but 2 toppings, hot fudge and caramel. How many different sundaes could she make? Well, 1, 2, 3, 4, 5, 6, 7, 8 is my guess because as I make this grid, I set up this grid so that I can record all of the possibilities here. And if I've set it up neat and tidy, like I have here, these open cells tell me that there's something that's going to logically fill up that table. So let's see what we do here. We have chocolate and hot fudge. We have vanilla and hot fudge. We have mint and hot fudge. We have coconut and hot fudge. For the second one, we have chocolate and caramel, vanilla and caramel, mint and caramel, or mint chocolate chip, I should say. And then we've got coconut and caramel. Hope that you see what a wonderful way probability tables can help organize our data. They help us to analyze what we've got going on a little bit more carefully and completely once we've got the data set up like this. Very easy for us to see trends in what is happening with our data or our problem-solving situation.